So, good morning. So we'll start the study of the statistical mechanics of quantum ideal gases. And so, so first, let's recall what a quantum ideal gas is. Okay. So the ideal part we know is that there are no interactions. Okay, and the quantum aspect is that we will, of course, we will do exact counting, etc. But we will take into account the statistics. So the whether the particles are bosons or fermions are input into the story, and of course the bosonic ideal gas and the fermionic ideal gas have completely different properties. Okay, and so this is what we want to do, and we will study the physics of these two things. And so we already have studied bosonic. So we already done the case of massless bosons. Okay, so now we will consider all our particles will be massive and non-relativistic. Okay, so what does that mean? The energy would be just p squared upon 2m, where m is the mass of the particle. Okay, so this is the dispersion relation. Okay, so then we can just work out the single particle density of states in the semi-classical. Approximation. Okay, and that's very simple. It's just that we just have to and we have to input the constraint that the energy is in the range in a certain range, or in momentum is in. So we'll stick to momentum. We'll see in a moment why. Okay, so the x integration, what will it give? So it's a gas in a box of volume V. So the x integration will just give us a volume factor. Okay, so this will be equal to volume, and since the energy is only a function of the magnitude of the momentum, we can integrate out the angles, so that will give us a 4 pi integral p square dp upon. Okay, so what we will see is that we will just write so 4 pi v p square upon h cubed is like a rho of p. Okay, of course from that we can work out what it is in terms of energy. So let's do that also. So p, so epsilon equal to p square upon 2m, and so this is equal to, implies rather, p equal to square root of 2m epsilon. So let's just do this. D epsilon will be 2p dp by 2m. So this is just p dt. Okay, so this semi-classical integral will just become 4 pi v by h cubed. Okay, times so now p dp by upon n. So p dp, which we have here, we should replace it by m d epsilon. Okay, but there is another factor of p, so that will be square root of 2m epsilon.
Sir, divided by, right?
What is divided by?
MDE divided by under root 2ME, right?
Uh-huh. Why should I? 1 second, just p is root. I'm substituting here, right? P dp is md epsilon. Okay, and p is
Divided by P.
where am I dividing by p? This is okay.
Okay, okay, okay.
So I want to extract out the condition that it's energy. So this here the integral is over p. I want to convert it to an integral over this thing. So then I can we'll get something like this: 4 pi v by h cubed m power 3 by 2 into epsilon power half e epsilon. Okay, so rho of epsilon is 4 pi v m power 3 half by h cubed epsilon power half. Okay, so there's a density of states. Okay, and there might be, okay, so this density does not include the degeneracies. So for epsilon, so if there is a, things like spin degeneracy include degeneracies such as those involved in spin. Okay, there might be others also. So we'll just, what we will do is we will call that G. So it will be an overall multiplicative particle space thing. So if you have like a spin 0 particle, there's no spin degrees of freedom. So G would be 1. So G equal to 1 for spinless bosons, spin 0 or spinless. G equal to 2 for spin half fermions. G equal to 3 for spin 1 boson. And so on and so forth. Okay, so if I want, so later I'll put a G, and this is what depending on the example we need to put that. Is that okay?
So is there a root 2 missing in that expression?
Yes, there's a root 2 missing. Thank you. Let's absorb this also. Is this correct? 4, I absorb the 4. No, I'm now messing up, right? Root 2, 4, 2 will go, and there still be a 2 remaining. Okay, now you're fine? Okay, good. Yeah. Okay, good. Any other questions or comments? Okay, so now we are ready to do our computation. So, and what we will do for the moment, we will just write a formula which is true for both. So let me just. So we will compute log of q where Q is the grand canonical partition function. So what is Q? Q is pi over all states 1 by e power. Okay, so I said that every state, you think of it as a box, and we have done this computation, and Z is where Z is just e power beta mu chemical potential. And what is the answer for fermions? We have worked this out before.
One plus Z e to the minus beta e.
That's it. Okay, is this okay? So this came from, recall, this is from summing geometric series. And this is just, in a box you can have 0 or 1 only, no, just a sum of two terms. You pick a particular state, and okay, so once we do this, we can compute log. Maybe I'll write this in yellow. Log Q will then be okay. This minus n comes because there is this power here. Okay, so now we can do. So now we can carry out. So now we can actually not carry out, replace sum over states by G, which is a degeneracy factor, integral rho of E epsilon energy okay, in the above expressions to get. So this is a semi-classical computation which we just did. Rho we just wrote out there. So we get log of Q equals to, okay. And I want to just massage this rho in a particular fashion. So let me just do that here. Sorry, I'm going back and forth, but okay. So let's just define lambda, de Broglie wavelength, to be h upon 2 pi mjbt power half. So should I do it now? No, I can do it later also. Okay, let's just leave lambda here. It's just a thermal wavelength. So right now I'll just write whatever I have. 2 pi v Okay, so the first term is for bosons and second term is for non-relativists. Okay, is this okay? Hello?
Yes, sir.
That's
Yes.
perfect, right? No issues with any of these things. Okay, but there is a subtlety which I'll now discuss. So, to discuss that, I'll say what are the allowed values of the fugacity. I'll ask it in this fashion. And for that, it's useful to look at the, let's not worry about, let's look at the formula with the sum over states, which before we replaced with these things. And so, if you look at the case of bosons, you look at, for bosons, the ground state, okay, it has energy epsilon equal to 0, okay, contributes or is proportional actually right. I mean, see here, epsilon is 0, the energy, so you get log of 1 minus z, which is divergent at z equal to 1. You agree?
Yes.
Okay. So, and z was e power beta mu nu. So what we will do is we will say that we will restrict z to belong to the region, 0 is allowed of course, to 1, and here we don't know whether 1 should 1 be included or not. Okay, so I will say that 1 has to be included, we will see in a moment, but okay, so we'll put it in this region. Okay, so including 1 is to be explained. We have to understand that. So with this parenthetical remark, I will say that we have to include it, but we will see it in a moment. Okay, so this is what we get. Okay, so there is a log 1 minus z divergence. Okay, so, and you can see that, so what does this mean for mu? Negative. Z equal to 1 is 0, which is a limit point. You agree? Z is e power beta mu. Is this okay? Somebody respond.
Yes, sir.
Okay, good. Okay, so mu is always negative. Now let's look for fermions. There is no such restriction. Okay, so implies that mu can take any value, take any real value. Both positive okay, so we need to refine this log q, where we wrote this integral by itself. The integral doesn't have a problem, but there is a divergence, and if we try to keep track of that, okay, so Yeah. Okay. So we need to handle.
So,
Yeah.
can mu be zero for fermions?
No. Mu can be zero for fermions. Yeah. It can be negative. It can be positive.
Okay, sir. And can you explain once again why it is negative for bosons?
Because z is e power beta mu, and z is between 0 and 1. So z go equal to 0 is mu is negative infinity, and z equal to 1 mu is 0. So, and it's a monotonic function of z, of mu rather.
Yeah,
That's all.
okay, sir.
There's nothing deep,
Thank you.
nothing. It's not very deep. So mu is always negative, and this thing. Okay. And just a remark is that the ideal gas, the chemical potential of the ideal gas was negative, right? Classical identity, where we didn't do anything. Okay, so what we can see is that whatever we get, at high enough temperatures, low densities, we will see that the equation of state, etc., of the quantum gases should agree with that of the ideal gas. This is something which we know, and so this is consistent. So there is no, I mean, mu being, if we found that the quantum bosonic gas said that mu is always positive, then there is then there is no limit where the quantum boson gas would agree with that of the ideal gas. Okay, so this is just a remark. Okay, so now so that so we need to treat the epsilon equal to 0 contribution a little carefully. Okay, and we'll see what that is in a moment. Okay, so yeah. So I hope you recall that we had proven this PV times KBT was equal to log of Q. Okay, so let us now, so this will imply, okay, so now let's just do bosons first. Okay, so for bosons, this implies P by KT KBT is 1 by V times log Q, but we have worked out what log Q is. Okay, we have this term minus G into 2 pi into 2n power 3 by 2 divided by h cubed integral okay. But now like I said, let's look at what we had before we took the this thing. So it just said that it was sum over states. So we have to take care of the contribution of the epsilon equal to 0. That gave minus. So we'll write that separately. Okay, so this is just taking care of divided by V. Is this okay?
So is that case not included in the integral when we take the lower limit as 0?
Yeah, so we just, it's an integral and we are writing something from 0 upwards. Okay, so we will just say that you start, I mean, you would say you should correctly write it as some delta little bit greater than 0, but if you're taking the thermodynamic limit, that will tend towards 0, so it shouldn't matter. Okay, but so we will see what is, so I'm writing out this explicitly. What we have done is, what we actually have, the correct statement is that if you did the proper quantum thing, it will be sum over various things, right? So we're using the semi-classical thing, but the semi-classical thing, what I'm saying is, we may not see this singularity properly. Okay. So I'm putting this in, but you will see, I will argue that why usually we don't have to worry about this term. This term won't be there. Okay. And why? Okay. So there are, so let's look at the extra term. Okay. So the term, so as long as z is less than 1, doesn't matter what it is. Okay. The term vanishes. And this is thermodynamic limit. Okay. So like I said, but if you want to include z equal to 1 in the considerations, then what you have, then this term may not vanish in the is indeterminate, because numerator is infinity, b is also going to infinity. This term may not vanish, rather it's indeterminate at this point.
Hello.
Yeah.
Sir, but as even z approaches 1,
Not
like,
approaches
gets,
1,
like,
equal
very
to
close.
1. Equal to 1.
Sir, but even if it approaches 1, like 0.99999, like that.
Yeah, but thermodynamic limit is, it's still finite. And we're taking
So
strict
won't
b.
it blow up even then?
No.
Okay.
Because, I mean, thermodynamic limit is taking v to infinity. And
Okay.
if you said 0.99999, okay, so something like that, log of that you compute, whatever that is, okay, it will be, some, so if 0.999 to some 6 decimal places, then it will be some 10 power. Log of that will be around, log 10 times 6 or something like that. Not, okay. So, but what I'm saying is that mathematically speaking,
Yes,
mu is a fixed number, right? So when mu is such that z is not equal to 1, but when it's equal to 1, then you have to worry about, then you have to, then you can't decide. Okay. And we will see how to do this. So just before, and you can write a similar formula for fermions, where this minus sign won't be there and this will become plus. And there's no need to write this extra term. There's nothing singular happening. Okay. So let's work out what is the number density. Okay. So that is, let me actually define some functions here, and then we can come back to number density. Okay. So let me define, we have this integral, and what I'm going to do is, first thing is, let's make a change of variables. Using a change of variables rather. Okay, so we'll do that. And so what is that? So what I'll do something very simple. I mean, I'll just say that x equal to beta epsilon. Okay. Okay, so this implies that d epsilon equal to kBt times x. Okay, and x goes epsilon goes from 0 to infinity, x also goes from 0 to infinity, so limits will be fine. So I just have to rewrite this integral. So what we will get is I'm very inconsistent with how I write x. Okay, so we just so what we'll see is that the d epsilon out here will give a factor of kBt, and also epsilon power half will give a kBt power half. Okay, so we'll get a kBt. So in the process of replacing these with x's, we'll get kBt power 3 half, which I can absorb into this. Okay, so we'll get p upon kBt equal to minus t 2 pi. Okay, there was a m power 3 half, and this m or 2m? 2m power 3 half, so it is 2m kBt power 3 divided by h cubed. Okay, integral okay, so this is what we get. Now recall I defined I want there's a v factor I forgot. Let me define lambda to be
So v won't be there in the first term because we divided by v.
thanks. Two pi okay, so if you look carefully we can trade this h.
In the previous expression, won't it be,
Yeah, what will it be?
sir?
Yeah.
So in the previous expression, it will be 2m kBt 2 power 3 by 2.
Yeah, thanks. Okay, I would have sworn I wrote 3 by 2, but anyway, so you can see that this 2m kBt etc. So let me just do something. So there's 2 remains. There's also this pi if I put here, so you can write this as g into okay g by lambda cubed into a quantity which I'll write out now. There's a 2 here, and I put a pi. I made a pi power 3 half to make it lambda cubed, so there will be one power of root pi missing. There's a minus sign. Okay, so this square bracket called it's some integral now, okay, which is only a function of z. Call the term, oh man, call the term in square brackets as g 3 by 2 of z. with the minus sign, etc., etc., etc. Okay. So so these integrals, okay, so integrals of this variety, okay, are called Bose-Einstein integrals. Okay, I wrote a 3/2 and are defined as follows. Gn of z is defined to be 1 by gamma of n Okay, so that's what you get. And there were additional property. So there are many properties. So yeah, that z d by dz of gn of z equal to uh, what is it? Z d by z dz gn of z is equal to gn minus 1 of z. Okay, and then for small z, for small z, gn of z goes as z. Okay, and gn of 1 is just some. You can prove all these things, okay, these properties. L equal to 1 to infinity 1 by L power n, which is zeta of n. Okay, so in fact you can do better than this. You can write you can write a okay, so this is what we get. So now we are able to write P by kBt will be G times G3 of half, is it? G by lambda cubed times. Okay, so now we also want to work out what is the number density. Okay, so so the way we would do that is to go back, and so we have to do, it will be so n is up to factors of this thing is d log q by d mu. There's some kbt factor. Okay, so let me put that also. Right, but what is d by d mu? Little bit of algebra will show you that that is nothing but z d by dz. Okay, can you change of variables? You can check that. So this is equal to kbt d. Okay, so but we have formula for log of q. So I wrote p by kbt, but this is equal to, but this has another role. This is equal to v times 1 by v times log q, right? Okay, so we have a formula for, I forgot something. Okay, so this is what we have. So let's just do this thing. So we get n by v. Is a KBT there or not there? It is there, right? Yeah. Nope. There's no KBT. Dimensionally, it's off. Okay. This is better. Okay. So this is what we get. So now we can just do this thing. So what is, so we get V, GV by lambda cubed. What happens to G3 half by Z? Look at this property that we wrote out. Nobody complained. G3 half, this doesn't, there's no logarithm here, okay? But this is exactly what you can do is you can integrate by parts and show that this will become this guy with 3 half for n equal to 3 half exercise. We did it last class for photons, right? We had a log and I did integration by parts, remember? So it's the same thing. So we use this z d by dz, or gn of z is just gn minus 1. So this will be g half of z. Okay, and log will be log of this thing will be plus. Remember, it is z1 by z d by dz. So okay, okay, is this fine?
Sir, log Q is dimensionless, right?
Which one? Yeah,
Log Q.
log
So
q.
KBT, I think KBT will have to be there.
No,
So that
n is also dimensionless.
so beta mu will be
So there is
dimensionless.
kbt. See, n should be dimensionless. So lambda cubed and v, lambda cubed and v, lambda
So
lambda cubed and v will make it dimensionless. So maybe I'm assuming that G3 doesn't have dimension. So just give me a second. Let me just. I'm slightly. No, if you go back to first principles, we can just derive this, right? What is, this is, n is just expectation value of this thing. So Q would be sum over all states, right? E power beta epsilon times Z power the number, right? So d by d mu of Q would be sum over states. So you take d by d mu of e power beta mu, it will pull down an n number of particles. And if you divide by Q, that will give you the probability. Right? Is that clear? Unless I've forgotten something in log Q. My log Q, go back to my log Q expression. Because I've got all, I mean, G is dimensionless, we agree, right? X is a dimensionless quantity. All the powers of beta have come. I'll let you explain this, maybe. Okay. So I have a formula. Okay. So V by lambda cubed, you agree, is dimensionless. Lambda is the thermal wavelength. So lambda cubed is volume, same dimension as volume. So V by lambda cubed is dimensionless. G, just as we discussed, G of Z for anything is dimensionless. Similarly, Z by 1 by Z is also dimensionless. If you multiply by KB of T, I get left hand side is N is number, which has no dimensions. KBT has dimensions of energy. Who was objecting?
No, sir. I think I'm making a mistake.
Yeah. Okay. So, I mean, the thing is, you should go back. I mean, correct statement is, if you remember in terms of phi, okay, phi is minus KBT log Q. So, d phi by d mu is actually mu by KBT. It's not mu. So, there's a KBT factor coming, which you have to get rid of. Okay, if you're doing in terms of the, the free energy, right? The grand potential or whatever, there's a KBT, but I just work directly with log Q rather. Okay, so I think what I have is correct. Okay, so this is what we get, and so this formula is important. This formula, or we can write this as N by V, which is the number density, is equal to G half of Z plus Z into 1 minus Z. 1 by V. Okay, so this equation, so the thing is that if you are given the average density, which is N by V, this formula gives us an implicit equation for mu. Okay, so you have to solve this equation, and then you get the answer. Okay, and then you have to check if mu is negative, then you're okay. So next class we will see that there is an issue. By the way, I'm a little puzzled that I got G half, but just give me a second. I wrote some property, right? I'll check my property. Is that correct? Z, I wrote something about, sorry, where are these properties? Yeah, so I said Z d by dz. Okay, so then that will give, oh, there is some little bit of work to do. So I'll put a question mark here. Okay. Is this correct or wrong? I don't know. Okay. Z d by dz is d mu, right? Okay. But anyway, let's discuss it next class. Okay. So we get this formula. We get an equation of mu. Okay. So we will now, next lecture, we will see how to handle Z equal to 1. Okay, and when Z equal to 1, what we will find is that a macroscopic fraction, and that would correspond to this quantity here having a finite number. So you just go ahead, replace this in the thermodynamic limit with some finite number of particles in the ground state. Okay, so I'll stop here and pause for questions.